Good evening to all. This is our 27th lecture of the course. In the previous lecture, we have started our discussion on the diffusers, and particularly for diffusers, we have seen actually multiple configurations, and out of all these configurations, we said that typically two configurations are very important. In one of the configuration, we have a test section, and then immediately after the test section we are having a diverging section. So this is one configuration, and another configuration which we have seen is, if we have a test section, then in this particular test section first we will be having a converging section, then we will be having a throat, and then we will be having a diverging section. Okay, so in case of first type of diffuser, we observed that just at the exit of this we will be having the formation of a normal shock wave over here, and then we will be having actually on the downstream of this normal shock wave my Mach number will be less than 1, and then further divergence will be actually resulting in further decrease in Mach number, and at the exit our Mach number will be very small, less than 1, and this is the reason if P infinity is the pressure over here, that will be nearly equal to P naught infinity for this case, and which mostly we want our exit to be at say 1 atmospheric condition. Okay, then for second type of diffuser, we saw that in this type of section we will be having formation of actually the oblique shock waves. Okay, and these oblique shock waves will keep on reflecting from the boundary and then will form a number of shock waves, and particularly because at the throat we want our Mach number of the flow to be 1, and after this just we are having one divergence. So here we may find the other wave formations, some weak waves over here. So say we may have one weak wave, weak shock wave over here. Okay, so the difference between two configurations is that here this initial strong normal shock wave is majorly responsible for the decrease in the Mach number, and here we have number of oblique shock waves, and then we have a weak normal shock wave. So obviously from our earlier understanding we can say that in comparison to case number 1, in second case we will be having low loss of stagnation pressure. Okay, and this is the reason that for majority of the application we may target using this configuration. Okay, and in order to make the relative comparison of these two configurations, what we have done basically, we had defined one parameter which we called as diffuser efficiency, and efficiency of the diffuser, we mentioned that it should be eta d, that is equal to, say if here my delivery pressure is Pd, so corresponding to that my stagnation pressure is say P naught d, and here if my initial pressure of the reservoir is say P naught. Okay, so then my diffuser efficiency will be, because this is the typical configuration which we will be using for majority of the diffusers, so for this configuration the ratio of P naught d divided by P naught actual upon, for this particular configuration, if this is 0.1, this is 0.2 across the shock wave. So say P01 is the pressure over here and P02 is the pressure over here. So it has been found for this type of configuration that whatever is my stagnation pressure ratio of exit to reservoir, that is nothing but equal to the stagnation pressure ratio across the shock wave. So that is the reason that I can simply write P02 by P01 for normal shock wave at which condition? If say ME is the my desired Mach number in the test section. So at ME. So whatever we will be getting this number, that we call as nothing but the diffuser efficiency. Okay. So our expectation is that because here we will be having more loss of pressure, and here we are expecting less loss of pressure. So our expectation will be that this configuration will perform better in comparison to this configuration. So that is our expectation. So it means that we must find in majority of the cases we must find that my diffuser efficiency should be less than 1 or greater than 1. Is this bigger or this one is bigger? ऊपर वाला, yeah. So what we have in majority of the cases, we will be okay. Let me put it in a different way. So if I write this as P naught 1 by P naught 2, then what will be happening? P naught 1 by P naught 2 will be always larger than that. Okay, so that will be always larger. So if in any configuration this ratio is equal to this ratio, then my diffuser efficiency will be 1. Okay, so what we find that for moderate Mach numbers, okay, for moderate Mach numbers, we find that our diffuser efficiency is actually high. Okay, so it means that for moderate Mach numbers, my converging diverging diffuser will perform better. But in case of very high Mach numbers, if you want your M exit to be very high, in case of very high M exit, we find that normal shock wave type of diffuser is having actually better characteristics in comparison to that of a converging diverging one. Okay, so this is the main conclusion which people have found by doing multiple experiments, that for moderate Mach numbers we find that convergent divergent type diffuser, this performs better. Okay, this performs better in comparison to that of a shock wave type diffuser. Whereas for very high Mach numbers if we go, then our normal shock wave with diverging section, this performs better than convergent divergent diffusers. So this is the typical observation from different experiments. Okay, so because now what happens, basically it is expected that normal shock waves should perform less, because that will be resulting in more loss of pressure, and convergent divergent should perform better in all the cases. But this particular conclusion is based on the assumption that viscosity of the fluid is negligible. When viscosity of the fluid in physical scenarios, real scenarios, what happens? Viscosity of the fluids comes into picture. So particularly at very high velocities, viscous effects becomes dominant. This is the reason that their normal shock wave type of diffuser section works better in comparison to a convergent divergent diffuser section, which is having a weak normal shock wave, and that is also actually followed by a number of oblique shock waves. Okay, so this point should be made very clear that our expectation is that, because in case of normal shock wave, total loss of stagnation pressure is more, so that should have least performance if we consider the ideal situation, that is non-viscous system, inviscid system. Okay, so that is the normal expectation based on our theoretical understanding, but particularly for inviscid system. But in real scenarios, because fluid viscosity also comes into picture, so basically viscous effects dominate for convergent divergent type of diffusers, particularly at the high Mach numbers, and this is the reason that diffuser section with the normal shock wave and a diverging section works better in comparison to a convergent divergent section, particularly at high desired Mach numbers. Okay, now one important aspect is that if we have this convergent divergent diffuser section, then basically we will be having two configurations. One convergent divergent section we will be having for nozzle, and one convergent divergent section we will be having for diffuser. Okay, and in between these two, this is our test section. Okay, so at the test section my Mach number is m exit, and say this is my first throat having area 81, this is my second throat having area 82. Okay, now this is also desired that at this my Mach number will be equal to 1, I will be having sonic condition, and at this throat also my Mach number has to be equal to 1. Okay, so now if you see, situation is opposite. How different? Here if you see, initially flow is subsonic, so in this portion Mach number is less than 1, and then it is approaching 1 at this particular throat point. And in case of diverging section, here Mach number is greater than 1, and then it is achieving the sonic condition over here. So as though we are having two throats, so throats are just kind of doing the same purpose, means in case of both the throats I should have sonic condition at the throat. But if I see in case of first throat, just before it I have a subsonic flow situation, and on the other hand in upstream of the second throat I have a supersonic flow situation. Okay, so it means that flow is approaching with different conditions towards the throat. So that is the reason that our areas 81 will not be equal to 82. Okay, so 81 area will not be equal to 82. So now it becomes important to understand what will be the relation between these two throats. So if I use a wind tunnel which is having a convergent divergent nozzle and a convergent divergent diffuser, then what should be the relation of these throat areas which can actually work for this situation? Okay, so to derive this relation, one thing we can do, I can write down the mass flow rate as nothing but equal to density times area times velocity. So if I write this mass flow rate at throat 1, so at throat 1, because my condition is sonic, Mach number is equal to 1, so say my density is rho 1 star, area is 81. Okay, area of the first throat is 81, and corresponding to this velocity is say v1 star. So this will be equal to, because mass flow rate is equal, rho av has to be equal, so this should be equal to the conditions at second throat. So at second throat I have rho 2 star into 82 into v2 star. Okay, now as I know that my Mach number at these 2 points will be the same, so I can replace this v1 star with a1 star, okay, and v2 star with a2 star. What is A1 star and A2 star? A1 star and A2 star are nothing but the speed of sound corresponding to the sonic condition at this point. And I know that for a calorically perfect gas, A1 star will be equal to gamma R T1 star square root. A2 star will be equal to gamma R T2 star square root. Okay. Now if you see the flow from point A1 to A2, flow from point A1 to A2. So say this is my condition 1, this is my condition 2. So 81 and 82. So flow from 81 to 82 is nothing but a adiabatic flow. Because in this flow I am not adding any heat, I am not removing any heat. So flow from 81 to 82 is nothing but the adiabatic flow. And we know that if our flow is adiabatic, in that case T1 star will be equal to T2 star. Okay. So this is the reason that A1 star has to be equal to A2 star for adiabatic flow. So I can cancel out A1 and A2 star. Okay. So from here what I will be getting? I will be getting 82 divided by 81 equal to rho 1 star by rho 2 star. Okay. Is this point clear? Now, as I have already used the assumption of calorically perfect gas, so for calorically perfect gas density, I can write from ideal gas equation as P by RT. Okay. So, what will be happening from here? 82 by 81 will become equal to P1 star divided by R, T1 star divided by 5. Now RT1 star and RT2 T1 star and T2 star are the same, so I will be getting simply as P1 star by P2 star. Now another important point is that we know that P naught by P is equal to 1 plus gamma minus 1 by 2 m square whole power gamma by gamma minus 1. So if I have to calculate stagnation pressure corresponding to the two throats, so corresponding to first throat, I can say that P naught 1 divided by P1 star will be equal to 1 plus gamma minus 1 by 2 into 1 square, because at the throat Mach number is 1. This whole power gamma by gamma minus 1. So if you calculate this, it comes out to be gamma plus 1 minus 1 by 2 plus 1 by 2. So gamma plus 1 by 2 whole power gamma by. Okay. Similarly, corresponding to second throat, I can calculate P02 by P2 star. That will be becoming equal to once again gamma plus 1 by 2, because there also Mach number is 1 divided by power gamma by gamma minus 1. Okay. So from here I can simply say that P01 by P1 star is equal to P02 by P2 star. And this simply means that P01 by P02 equal to P1 star by P2 star. So now I can replace and substitute over here. So what I will be getting ultimately from this, that 82 by 81 is nothing but equal to P01 by P01 is the stagnation pressure at the first throat and P02 is stagnation pressure at the second throat. We also know that our flow is from first throat to second throat. So ultimately P01 has to be greater than P02, then only flow will be from left to right. Okay. So this is the reason that if this is 1, so ultimately my 82 is becoming P01 by P02 multiplied with 81. And as this ratio is greater than 1, so ultimately 82 has to be greater than 81. So this is another important conclusion. Okay. So the point is, if you use a supersonic wind tunnel to achieve Mach number, some supersonic Mach number ME, for achieving that, whenever you are using the convergent divergent section for a nozzle, then it will be having different throat area. And if you are using a convergent divergent section for a diffuser, it will be having different throat area, and throat area of diffuser has to be greater than nozzle, and this is the ratio of actually throat area. Okay, so now this is the actual theoretical throat area, theoretical throat area which we are actually getting from these equations. But ultimately we cannot exactly maintain this throat area. Okay, so there are some other issues, and because of these other issues actually we have to slightly keep this different than this value. Okay, so what are the issues, that also let's try to see. This throat area, one another important point is this throat area, whatever we have calculated, this we calculated by considering that my test section is already having Mach number at the desired condition. Okay, so if a supersonic nozzle is already in operation, system wind tunnel is already in operation and giving us the desired Mach number, then my throat can work at this area. Okay, but we will be finding in the later portion that when we are just starting a wind tunnel, at that time we will face some other difficulties, and because of these difficulties we have to keep some different area for starting the wind tunnel. Okay, so typically let me show you the, if I plot the efficiency curve for a diffuser. So efficiency of a diffuser with, say, I am plotting it with, say, 82 area of second throat. Okay, so over this, say this is my point, this is my 82 area which I have obtained from the previous equation, that is, this is equal to P naught 1 by P naught 2 times 81. So this is the value of 82. So on this side 82 I am wearing, but this is the value of this one. Okay, so this is one condition. Now another condition is that, okay, so if I see typically the efficiency of a diffuser, so at this area, just slightly above this area, I will be finding the highest value of the efficiency. Okay, and if I go below this area, then I will be finding that efficiency is having a significant fall. In this portion, efficiency is having sudden fall. Okay, on the other hand, if you keep on increasing the area, then you will be finding that your efficiency will keep on decreasing. Okay, this is one important point. What I am saying is, we have found some area over here from this equation. So whatever this area I have found, just for the area of second throat, which is slightly higher than the area we have found from this equation, we will be finding for that we will be having a highest efficiency. And if I decrease the area from this, then my efficiency will be having sudden fall. Okay, my efficiency will be having sudden fall. Why? Can you tell me why there will be sudden fall in efficiency? So what I am saying over here, say this is my 82. Okay, so if I decrease 82, what will happen? This is one situation. Another situation is, if I keep on increasing 82, if I take larger value of 82, then what will happen? This is quite evident. If I increase the value of 82, what will happen? Ultimately, this convergent section is providing me over here a sonic condition. If I increase throat area, here flow will be, if I increase area, then flow will be supersonic. And due to the supersonic nature of the flow, I will be finding that in the diffuser section, there will be occurrence of a strong normal shock wave. So as I am having a strong normal shock wave, that leads to significant drop of pressure over here. So that is the reason that if I keep on increasing the area, my efficiency will keep on decreasing. Okay. Is this point clear? If you increase the area, at this point, you will not be able to maintain the sonic condition, which is the desired condition. Okay. So ultimately what will happen? Ultimately, we will be finding that, uh, just over here, we will be having the formation of a shock wave, and that shock wave will lead to significant drop in the pressure. Contrary, here if you decrease the area, so this is the area which is required. If you further decrease the area, ultimately it has to give here the sonic condition only. Okay, so we will be finding that after this point flow choking will happen. Okay, so due to that we will be experiencing over here a sudden fall of the efficiency. Fine. So it means that to maintain the highest efficiency, we have to maintain the area of throat slightly higher than the area which is obtained from this particular equation. Okay. However, there is, say, in terms of if I keep the throat area very large, then I will be having decrease in efficiency. Okay. But this particular area of throat, whatever we are calculating, this is calculated based on the assumption that already my wind tunnel is in operation and I am able to achieve a Mach number of ME. Okay. But here one operational issue comes. The operational issue is when you are going to just start the flow. Okay. So what will be happening? Slowly you will maintain the pressure loss, desired pressure drop. So all of a sudden this will not happen. For example, if you switch on a fan, if you switch on a blower, so when blower will start rotating, it cannot immediately achieve its full RPM. So slowly it will be achieving, and also slowly flow will progress within the pipe. So during the transient operation of this particular wind tunnel, what happens? We experience that at nozzle section, whenever the flow is increasing, there is formation of a shock wave. Okay, and that shock wave has to first travel through the entire section and leave out of that section in order to reach a steady or desired Mach number condition. Okay, and ultimately it was observed experimentally that for moving that shock wave during the initial transient phase of the wind tunnel, in order to move that normal shock wave out of the complete diffuser, we have to keep this area A2 higher than the area which we are getting from this equation. Okay, so ultimately in order to initially overcome the transient issues which are coming during the transient operation, our area required will be somewhere over here. So this will be, say, 80 to 82 dash needed in order to make starting of the wind tunnel happen. Obviously it can start, but starting of the wind tunnel happen at desired supersonic flow conditions. If you keep area less than that, then your normal shock wave will stuck at the second throat section and it will not pass this section. Okay, so if it is stucking at this section, it will not give you the desired conditions. Is this point clear? So experimentally, what is observed? Experimentally, it is observed that when we just start a wind tunnel, then a normal shock wave initiates at the nozzle section. That shock wave keeps on traveling, and that particular diffuser section or second throat must have some area 82 dash, which is considerably larger than the area which is required for maximum efficiency of the throat at steady operation. Okay, once the nozzle has once the wind tunnel has started. Okay, so that is the reason that starting area has to be higher. Okay, so now when you are designing a diffuser, so basically you will be able to design for maximum efficiency only if the operation of the diffuser is starting. Okay, so ultimately we design the diffuser for area 82 dash, so that our operation can occur. So shock wave, initial transient shock wave can go out of the system, and then we should be able to achieve the desired steady operation. Okay, so that is the reason. So now if you see, our operation point is somewhere over here. So normally diffusers which are having fixed area of the second throat, these diffusers operates at efficiency lower than the highest possible efficiency of the diffuser. Okay, so this is one operational challenge. Now there are some sophisticated diffusers where you can have some mechanism to have variable area of the throat section. So you can have some additional arrangement which will give you the area of the throat equal to 82 during the starting phase. Okay, and once the complete flow has been established, then by some mechanism you can actually decrease the area. Okay, you can decrease area and then go towards the highest efficiency point. But such type of actually designs of diffusers are very complicated, and these also are costly. Okay, so considering the economics and complications of this area, for majority of the applications actually majorly diffusers are operated at certain conditions which are other than the highest uh, efficiency conditions. Okay, so if it is not operating at highest efficiency, in that case what will be happening, basically the pressure ratio across the pressure ratio will be large between exit and inlet point, and you have to supply more pumping power, so slightly higher operational cost it will give to you. Okay, however you will be able to achieve the desired operation. That point is clear. So desired operation can be achieved even with fixed area also. Okay, so majorly if you see from experimental conditions, so diffuser is actually very complicated system. So if you see, so it appears a very simple geometry, but whenever actual flow effect comes, because we are taking over here the assumption of quasi one dimensional flows, so when actual flows comes, then there are actually many complicated issues. So typically for a diffuser, the efficiency of diffuser is function of many parameters. So one of the function is ratio of 82 by 81. Second important function is desired Mach number. Third important function is flow angle, because when you will be putting some object in the test section, that will deflect the flow. So ultimately when the flow is coming to the diffuser section, that may also come at certain angle. So now we are assuming that in our test section, whatever object we are placing, actually that is not making any deflection in the flow, because ultimately we are considering the quasi one dimensional flow. But whenever we will be placing such object, that will also make some deflection, so we will be having some flow angle. Okay, and ultimately how much is the length of this second throat, that is also an important parameter in controlling the efficiency of the diffuser. So second important last important parameter is length of second throat. Okay, so from practical considerations, all these parameters are to be adjusted so that we can avoid the initial transient operation also, and then we can also operate the diffuser with maximum possible efficiency. Okay, so this is the reason that whenever people design the diffusers, it is generally said that it is more of an experiential art rather than the actual theoretical design. Okay, because whatever actual theory we are studying over here, that is for very selected set of assumptions. Okay, so if you have to go for detailed analysis, actually, then it is more complicated. Okay, so that is the reason that it is based on the experience, and it's more of an experiential art rather than using the detailed theoretical modeling or fundamental. Okay, another important point is most of the discussion whatever I have actually done over here related to the diffusers, that is specifically I have discussed by considering the case of a wind tunnel. However, diffusers are used in many other applications such as in jet engines, rocket engines. So in many sections, actually, you will many applications you will be finding the use of diffuser. So basically, whatever fundamentals we discussed over here, these are applicable for these particular applications as well. Okay. However, along with these theoretical fundamentals, for a specific application, we also require the knowledge of experience from the previous experiments and other studies in order to design the diffusers for certain applications. Okay, is this one clear? Now another important point is whenever we specifically talk about the nozzles, in case of nozzles, as I told you, that if we are able to maintain precisely the pressure which is required to have isentropic subsonic supersonic condition, then our flow will be free from shock waves. Okay, but in case we are having slight over expansion or under expansion in the nozzle, then we will be finding that we will be having formation of oblique shock waves or expansion waves depending upon whether we have over expansion or under expansion. So if you recall, particularly for nozzles, I have discussed you two configurations where okay, so say I have these two nozzles. So in first case, if I have over expansion, so in case of over expansion, this P exit, say this is P back pressure PB, so P exit will be lesser than, okay, in case of over expansion. So ultimately what will happen, I will be finding that here I will be having formation of a oblique shock wave. Okay, so and in this case you will be finding that say flow streamline will move something like this. Okay, on the other hand, here in second case, if my PE is greater than, so this is the case of under expansion, then I have to further decrease the pressure. So for further decreasing the pressure, I will be having a series of expansion waves starting from this point. Okay, so ultimately you can see that the reason immediately downstream will be having pressure PB, and just upstream the shock wave or upstream this one, we will be having pressure PE which is other than PB. So ultimately here if you see, this normal shock wave will keep on expanding. Okay, and behind the shock wave here I will be having pressure PE, and after the shock wave I will be having pressure PB, and away from everywhere also I will be having pressure say PB, say atmospheric pressure. So ultimately this shock wave is extending. Here pressure is PE and then it is becoming PB, and then this shock wave is interacting far away from this section. It is interacting certain boundary, and this boundary is nothing but a boundary of free stream pressure condition. Okay, so we know that when an oblique shock wave comes to a solid boundary, it reflects as an shock wave only. Similarly, if a expansion fan comes to an solid boundary, it reflects as an expansion fan only. Okay. So what we have to see now, if we are having one incident shock wave, if it is going to a free boundary, free pressure condition. Okay. So far stream pressure condition. So this I can also call as nothing but the far stream. This is far stream only. So any fluid streamline which is far away from our desired flow condition. Okay. So when it actually goes and meets a free stream, far stream, then what will be happening? That is actually important to study. Okay. So let's now first study the interaction of waves with far stream. Okay, this will help us in understanding that on the downstream of the nozzle actually what type of flow can come if we have over expansion or under expansion like situation. Okay, so typically let's consider that we have some incident shock wave, something like this. So this is my incident shock wave. Okay, and I have my flow which is moving like this. Say this shock wave has originated somewhere over here at this point from the bottom portion. Okay, so now I will be finding that up to this point if shock wave is expanding, so I will be finding that just above this everywhere I will be having flow as P infinity if this is the pressure P infinity. Behind the shock wave also I will be having pressure P infinity. But if any streamline which is passing through this, then that streamline will bend. It will bend something like this, and say if this is 0.1, this is 0.2. So here it will be having pressure P2 which will be greater than P1. Fine. But if I consider a streamline, which is just passing through the edge of the shock wave, okay, so that streamline will also deflect, but ultimately this streamline will be having pressure P infinity only, because this is just crossing the shock wave. Fine. So it is not passing through the shock wave, it is just at the edge of the shock wave. Is this one clear what I am saying? So I have an incident shock wave where before the shock wave pressure is P infinity. So ultimately my P1 over here is equal to P infinity. Okay, so P1 is equal to P infinity only. But when this shock wave will come, I will find some pressure P2 which is greater than P1. But above this particular line is having pressure P infinity and it is having pressure P2 which is greater than P infinity. Okay, so let me even, because this line is not passing through the shock wave, so let me consider that this line is even moving as a horizontal boundary, horizontal line. Okay, P infinity. Fine. So ultimately what is happening? This upstream flow is not facing any shock wave, but downstream is facing a shock wave. So obviously in this section I will be having different properties, and in that particular section I will be having different properties, and these two different properties will be differentiated through a line which is called as a slip line. Okay, and for a slip line to occur, what is the necessary condition? Yes, for a slip line, straight slip line to occur, pressure over here in this zone and in this zone has to be same. So what now our objective is, on the downstream of the shock wave I have high pressure. So ultimately this high pressure has to become P infinity. So it means that when this shock wave is reflecting, going to this free boundary, this has to reflect in the form of some waves which can decrease the pressure from P2 to P infinity. Okay, so what I will be finding? I will be finding that from here I will be having actually number of expansion waves which will gradually decrease the pressure. So maybe I have drawn slightly in a different fashion. Let me put it correctly, because it is interfering here a lot. So let's say our shock wave is like this. Okay, so if shock wave is like this, then flow will deflect something like this. Fine. This is how flow will deflect. So this is my point 1, this is my point 2, and here P2 is greater than P1, which is equal to P infinity. Okay. Now this shock wave, when it is touching this boundary, ultimately this pressure has to become equal to P infinity only, then only this straight slip line can exist. Okay. So it means that here I will be finding a number of expansion wave. So this will be my expansion fan, and this expansion fan will decrease the flow and pressure, and it will make streamlines parallel to slip line. So after these expansion fans, say this is my condition 3, so here P3 will be equal to P infinity. Is this point clear? So now you see the difference. If you consider a solid boundary, on a solid boundary, if you have one incident shock wave, it will come as an reflected shock wave. Okay, so from a solid boundary, if one incident compression wave is actually interacting with it, it will come back as an reflected compression wave only. But if you are having a free boundary or far stream, okay, so if your shock wave is interacting with the far stream, so it will reflect back in the form of expansion fan. Is this point clear? Okay, this is important to understand. Okay, now let's also try to see the interaction of expansion fan with the far stream. So once again, far stream is like this. It is going straight, and here pressure is P infinity, and then say I have a number of expansion waves. So say this is my expansion fan basically. Okay, so what expansion fan will do? If I consider over here, my condition is 1, so P1 will be equal to P infinity. Now through the expansion fan, I will be finding a streamline will bend something like this. It will go like this. Okay, and in the far stream also, say this is my streamline at far stream. So above this entire streamline I am having pressure P infinity. But when it has gone through the number of expansion waves, then this P2 pressure will be less than P infinity. Okay, now these are my expansion wave which are interacting with this far stream. So if in the downstream, it has to ultimately meet with this P infinity. So what should happen? I should have increase of pressure from P2 to P infinity. For doing that, what will happen? I will be finding that one wave will reflect from here, one will reflect from here, one will reflect from here, here, and these all will reflect in a compressing fashion and will merge together to form a single shock wave or compression wave. Okay, so this type of compression wave, what it will do, when the flow will pass through this, it will slightly deflect such that it is becoming parallel to slip line. I may not be able to draw it correctly over, and at the same point of time, at this point P3, pressure will become equal to infinity. So here I can see that if I have an expansion fan, that expansion fan is actually reflecting back as an compression wave. I am not calling it even a shock wave, because here in this zone it is becoming combination of multiple waves, and after this point it is behaving like a shock wave, but up to this point it is becoming a combination of waves which are actually converging towards a single. Okay, so it means this is nothing but a compression wave over here. So it means that if I have a far stream or free boundary, then if expansion waves are incident on that, these will be reflecting as a compression wave. Okay. Now let's see how this actually alters our phenomenon, or how it gives a particular type of flow structure on the downstream of the nozzle when we are having this type of occurrence of the waves. Okay, so typically what I can do, I can consider a nozzle and say this is nothing but an over expansion nozzle. Okay, so if I have an over expansion nozzle, what will be happening? Here I will be having one shock wave. Here also I will have one shock wave. These two will meet at this point and then will further refract and move ahead. Okay, then I will be finding at some point far away I am having pressure equal to P infinity. So say this is the point where I have got pressure now equal to P infinity. So where pressure has become P infinity, there this shock wave will now reflect with the free boundary, because up to this point pressure is different, but just after this point pressure is free stream pressure. So now after this wave cannot propagate because pressure is the same. If wave is there, then pressure has to be different on the two sides of the wave, but sufficiently far away from that we will be finding that pressure is actually equal to free stream. So I can say that this is the free stream boundary at which my wave is interacting with free boundary. So when it will interact with free boundary, it will reflect as an expansion fan. Similar is the case over here. So here also I will be finding an expansion fan. Now further this boundary, say this is my free stream boundary now. Now this expansion fan will interact with this free boundary and it will reflect back as a single compression wave. Similarly, this will reflect and form a single compression wave. Then this compression wave will further interact with this free stream. So what I will find that I will have this type of structure behind the nozzle, this type of structure I will have, and inside this, in converging section I will be in these sections I will be finding, in diverging section I will be finding shock waves, and in converging section I will be finding expansion waves. So I will be having a combination of multiple waves. Okay, and obviously, because when this is the section over here, in this section ultimately what will be happening, these shock waves will give me the difference in densities, difference in all properties like pressure, densities, etc. Okay, so this type of particular shape is called as diamond shaped flow field or flow structure. Okay, so what we are finding, that if you just take a nozzle, okay, and that nozzle is having ambient in atmosphere. Okay, so then, because I don't have any restriction from the side, if I put restriction on the side, then it will become case of reflection from a solid boundary. Okay, so right now what I am saying is, if my nozzle is directly doing exit in the ambient conditions. Okay, so in that case what will be happening, I will be finding that my compression and or shock waves and the expansion waves will keep on actually interacting with free stream, and we will be experiencing that we are having some diamond shaped flow field. Okay, but this is possible when we are having over expansion. Okay, when you are having under expansion, situation will be different. First you will be having expansion fan, and then you will be having the compression wave. Okay, so you can try drawing the flow field by your own, but ultimately structure will look almost the similar. Okay, so what you can do, typically people have taken nice imaging using the slurring photography. Okay, so people have taken experimental images using the slurring photography. So basically slurring imaging technique is used based on the difference in density. So if you are having some difference of density, then people can obtain an image of the flow field. So what you can do, you can refer to diamond shaped flow field for over expansion of a nozzle. You can search in Google and you will be finding the nice experimental images. Okay, and even you can try to find out some research papers, and there you will be finding that a diamond shaped nice flow structures are actually captured using the series of diamond shaped this type of flow field people have captured using the experiments. Okay, is this point clear? One important point I would like to highlight over here is that whenever we are having this situation, so in this situation here we have expansion, then in this particular zone we have compression waves, and then we are having a single compression wave over here. Okay, so this type of typical situation we have not yet analyzed. Okay, so till now whatever we have studied, we studied this type of situation, that if we have a shock wave and then expansion fan, then how to determine the flow properties at this point, that is something which we have done. But if we have this type of complicated situation, that first we have this type of compression waves and then the single shock wave, maybe we can handle this portion, but we cannot handle this portion at the moment with whatever the knowledge we have gained till this lecture. Okay, so maybe if time permits, then near the end of the course we will be studying one method called as method of characteristics. So for solving this type of situation, we will be actually using the method of characteristics. Okay, so once again I will come back to this point when we will be studying that particular method. Another important point is, till this lecture whatever we have studied here, we have employed mainly the integral form of the governing equations, and by using the integral form of the governing equations we have made our most of the conclusions. Okay, and particularly if you see the flows which we have studied, first was flow through normal shock waves. There we were having the assumption of one dimensional flow. Second, we have studied flow through oblique shock waves, there we had assumption of two-dimensional flow, and that two-dimensional flow also, by using some geometric transformations, by using normal and tangential components across the normal shock wave, we have finally employed the normal shock relations only, okay, by using some geometric transformation. So we have tried to made that flow also kind of analogous or simpler to one dimensional flow situation only. Then third important aspect we have studied in this particular section, flow through nozzles and diffusers, and in this section also we have actually taken the important assumption of quasi one dimensional flows. Okay, so for all these type of situations, because we are considering that at a particular cross section our flow field is kind of averaged, and we are only talking about the average flow field, that's why we were able to derive majority of our conclusions from integral form of the governing equations. Okay, on the other hand, when we will be dealing with the more complicated situations of two-dimensional or three-dimensional flow conditions, in that case what will be happening, properties at each and every point will be different. Okay, so we want some governing equations which can give us idea of variation of property at each and every point. Okay, so till now whatever variation of properties which we have studied, that we have studied based on the idea of, for a whole we are studying a unique value, okay, and we are using a control, finite sized control volume, and we are just trying to predict the properties, average properties at its inlet and exit. Okay, on contrary, in case of more complex flow situations, it will be important to predict the value of property at each and every point. So in that case we are not interested as a whole that what is happening in finite size control volume, but we are interested at each and every point in the flow field what is happening. So when we are interested in continuous, when we are interested in each and every point of the flow field about the variation of properties, rather than our interest is on say a finite sized control volume, then we have to actually go for differential form of governing equations. Okay, because differential form of governing equations are more generic, these are applicable for each and every point within the flow field. Okay, so typically maybe now time is not there, so in the next lecture we will quickly try to summarize the differential form of different governing equations. So we will use the first principle approach only. So whatever integral form we are having, from that integral form only, by doing some mathematical manipulations, we will first try to obtain the conservative form of governing equations and then the non-conservative form of the governing equation. So the essence of using the differential equations already I have discussed. Now from the next lecture onwards I will directly talk about the conversion from integral to the differential form. Okay.